we looked into parametric approximations for the finite horizon, but today we will do parametric for infinite horizon. So let us look into policy iterations. So what is the plan? Plan is we discuss the parametric approximation for infinite horizon using policy iteration, and we focus on finite state version. So we will discuss infinite horizon, but we will do it via finite state but alpha discounted, and states will be denoted by the current state by I and the successor state by j. And the system equation is denoted by transition probabilities Pij. So the probability of going from I to state j when the control u is applied. And the cost, so these are as usual, right? So the cost of the state control pair IU will be denoted by GI uj. And the exact form of the policy iteration will produce a sequence of stationary policies with cost functions that we believe will improve iteratively and converge in optimal number of steps, or the finite number of steps. Of course, there are convergence proofs, and we will skip those proofs. These proofs are there in the references. So let us recall policy iteration in terms of Q factors. So Q factors we know is suitable for use in approximations and simulation based implementations. Policy iteration has two steps. First is policy evaluation. So in this case the Q factors are given by this. So the current cost and then the cost to go with the policy mu, and it's from I to j. So this is our policy evaluation step. So here Q mu IU is the cost of starting at state I and using the control u at the first step. So this is the cost at the first step, and then following the usual policy for the remaining stages. And the policy improvement will be when you update your policy, where mu tilde will be the minimum of these Q values for various options for the policies. So this is the policy improvement step. We have policy evaluation step at the first step, and then we have the policy improvement. So policy evaluations, we do it for multiple controls that we have, and we will look at what is the Q value for this control, what is Q value for another control, and so on. So this gives us the estimate for the Q values for various control, and then here you take the minimum of all those Q values, and then you say, okay, let me update my policy for the state I to be the control for which the Q value gets minimized. So this is what we saw is the non-parametric variant, but what we want to do now is parameterize this. So build an approximation and that can predict these Q values. So as you can see, the parameter now is introduced here is R. As usual in the finite horizon case, things kind of extend here. So again, when we are building an approximation function, we need a data. It's because we will use supervised training. So our set of states IS, so here S stands for the sample. So let us say I have Q samples. So then I will have data with Q samples, and this data contains the current state I, and then the control U, and then the approximation of the Q values, or the estimate of the Q values, which acts like a level for us. So this is the training triplet. Now this training triplet, or the data, is generated, as I said, via some kind of simulations or Monte Carlo simulations you can do, and you see for current state this action, this is the estimated Q value from current state, this action, this is the estimated Q values, and you do it for large number of data, and then you essentially get a data set, and then you can use it to fit this approximation function, parametric function, on these data. Let's say you can do a least square fit, and as we have seen in the finite horizon case in the last class, we can do these approximations. Okay, so as I said, beta s is the label here, and you are trying to fit this parametric function Q tilde mu with parameter R, and it is learning to predict beta s. So you use optimization methods basically to gradient descent, maybe to solve this, to find this R. So this is what, as I said, for each IS and US, for each state and the control, beta s is generated at is. So this gives you data. Now, since we are dealing with infinite horizon, then then we want to know beta s is generated for how many steps in future, because it's an infinite horizon problem. So one possibility is that you do it for k number of stages. So the estimate of the beta s that we have is for k number of stages. So basically it's a truncated horizon where beta s is giving you cost estimate for only up to k stages. Okay, it's a discounted cost, obviously. So although it's an infinite horizon problem, the beta s will be calculated up to k stages. Okay, so that's what it says here. Okay, it says here that for each is and us, for a current sample s, let's say, beta s is generated starting at is, applying us at the first stage, and simulating a trajectory of states and controls using the base mu policy for k subsequent stages, only k subsequent stages. Okay, although it's an infinite horizon problem, but labels are kind of created. Now, so you may say, is this a good level trying to learn this, which only terminates after k stages? So that's a good question, because if k is large enough, then we are thinking that this is a good enough approximation of the q values for the infinite horizon as well. But if your k is small enough, this is not necessarily a very good level to build a prediction function like q. So this is something you need to decide, like how big will be this k for which beta s computes this k stage q values. So as I said, so beta s is a sample of qk mu. So this is like q values computed up to k stages. So that's giving us like kind of a terminal cost, as if it's like giving me a cost for k step finite horizon problem. Okay, so we are kind of using a finite horizon thing cost all to solve infinite horizon problem, but it is a discounted cost. Typically infinite horizon we don't use discounted cost, but here it's a discounted cost, and we are assuming that at the k step it's kind of very close to the converged infinite horizon values. So this is what we are saying at the infinite horizon q vector, which converges to the infinite horizon as k tends to infinity, right? So the q values that we actually observe when k tends to infinity, and the q values that truncates at the k, we are assuming that it's a good enough. We are not very far from there. Okay, and all this will make sense in here. Okay. So as I said, the number of stages k may be large or small that you use as a reference point here to train your model. So additionally, you may build some additional terminal cost function which may be added to compensate for the difference. So as I said, it is an infinite horizon problem, but our terminal cost kind of q value seems to be stopping at k, and so this difference may be kind of large if k is small. Because if k is small, then essentially we are approximating infinite horizon with a very crude finite horizon estimate. So so we can once we have this terminal cost approximations, we can compute the new policy by just kind of taking the minimum of the q tilde that we have, which is the parametric one. And so given a stage a current stage I, now it is approximate policy, so that's why we use tilde again. So now our approximate policy I at the stage, our approximate policy mu tilde at stage I will be the minimum of the of these q tilde. So these values of q tilde, as you can see, are the predicted values. These are predicted values because r bar is the parameter that we obtained via the fitting here, right? So let us assume that r bar is the one that minimizes this. Then once we put the r bar, then we get this this parametric function, and then we evaluate. So r bar is fixed now. You have learned this during training, and then for various values of u, you will see among these various predicted values of q tilde, for various values of u, what is the minimum one, and that will be the new policy for u, which we still call it approximate, so we put a tilde here. But this is how we update our policy. With the help of parametric functions, we believe that it's a cheaper way. So parametric functions, the whole idea is like out of all so many possibilities, these parametric functions will give us some cheaper way to compute through through so many possibilities of control and states. Yeah, so of course another possibility is like instead of looking at Q values, so Q values are kind of like cost values. It's just that it adds the current cost and so on. But Q values are the value, the actual values. But then what we can do parameterize is also kind of in this way, where we say that for current state I, so we can collect these pairs, like for current state I, what are the actions or the controls that we will take for the current state I, and we may fit this policy. We can build a policy approximator as well. Okay, so this itself. Here, what you see here is that we have a parametric functions to predict the Q values, but we could also build something that learns to predict the controls. Okay, not just the cost, but it tells me to predict. It learns to predict the controls. So this is something additionally you can do where you can fit this data as well. Okay, so this gives you an idea where you have approximations for both the values, which are the Q values, and the policy space, the mu. So it's possible that you may combine both these approximations, both value and policy approximations. So finally, we after the last policy evaluations, we get the final Q factor approximations, and in the online play mode, the policy can be applied using the final Q factor approximation, obviously. So after all this training with the data and so on, when you are actually implementing this, let's say to play a game or something, then obviously you will use the final Q. So in detail, like this is what these policies will look like. So basically, this is the Q tilde for the J, and then this is for going from I to J, and so on. So this is just a expansion of what we have done before. This is nothing but the Q values here. So we can do this, extend this for multi-step look ahead also. Okay, so we are doing it as one step because this is our one step, and then when we're looking at cost to go from J onwards. But as we know, in finite horizon case, we can do this multi-step look ahead. So basically, we not just explore I to J, but maybe J to K and so on. It's like 2-step or 3-step or more, and then look at the minimum of these. But of course, that is time consuming, as we have seen before. So you have to really search quite a lot for multi-step case, right? Okay, so now let us look into some algorithms. But first, some quick remark on these approximations. So Q tilde may use a variety of features that could be linear or non-linear, like neural networks if it's non-linear. A major advantage of linear feature-based architecture is that policy evaluation is a least square. So if it is a linear feature-based architecture, then it will be essentially a least square problem, and it has closed form solutions that we have seen in the last class. We can actually solve this in an actual formula is there to we have this inverse thing, right? So to solve for R. So when linear architectures are used, a variety of approximate policy evaluation methods with theoretical guarantees are also there for TD lambda and LSTD lambda and so on. So some of these you can see in these references, or I will cover in the second half. Exploration issues. Obviously, to generate this training data, I, U, beta can be challenging. Inadequate exploration can bias the Q factor. So when you are generating this data, then again, we have discussed this before, like what type of these training data you are generating. So is it not creating certain bias that you only go to certain states and actions a lot more, and you neglect some important states and corresponding actions? And so are those states going to be underrepresented, which leads to potential error in your policy calculations? So to improve the state space exploration, large initial states can be used, but again this may require using shorter trajectories because again, if there are large number of initial states, then obviously you may want to kind of only look into shorter terminal trajectories, right? Because you don't want to kind of do this because the simulation cost will be very high. So obviously introducing a terminal cost function approximation can help make the cost beta more accurate. So alternative exploration methods use off policy, like another policy is there, mu prime, which kind of visits the unlikely states more often. Okay, so we may add some additional policy mu bar, so just to ensure that more exploration is there. There are some issues with the oscillations. So approximate PI may not yield an optimal policy like the exact PI does, but instead produces policies that asymptotically approach optimality within certain error bounds. So since we are using approximate policy iteration, obviously we are expecting suboptimal results, and then generated policies may oscillate, meaning that after few iterations policies could repeat in cycles. So these are the things that are observed when you apply PI. Parameters vectors are associated with policies may oscillate, so the parameters themselves may oscillate. These oscillations are known as chattering and can be problematic with the guarantee of policy effectiveness. So these are like some real life observations. When you apply PI, then there are these issues. Okay, so now we discuss optimistic approximate policy iterations that involve Q factor. So these may involve only single sample or only a few samples between policy updates. These methods can be really good when you apply do have online play implementations, because the sample requirement is less because of the limited sample requirements. And however, the optimistic methods come with challenges that needs to be addressed. The very fact that you have like very small number of samples, that can create issues. And an example of such method is an extreme version of Q factor parametric approximation that uses just single sample in the policy updates. So yeah, so what are these? So let us see here. So simulate the next transition. So let us say you go from ik to ik plus 1 using the transition probabilities with the control uk, and generate the control uk plus 1 with the following minimizations. So then you will look for the minimization of the q tilde ik plus 1 and minimize over u. So in some cases, to enhance exploration, uk plus 1 is chosen with a small probability to be random element of uik plus 1, or that is epsilon greedy. So to ensure that that some exploration is there, you may not want to kind of always look into this absolute minimum all the time. So that allows some exploration possibilities. And what is the use of that? Because then when you are in a training mode, then you want these controls, you are exploring basically. So it's like the look ahead thing that we did previously in the finite horizon case. You do want to give some possibilities to kind of select other controls. So when it is the case that you are allowing with epsilon greedy, then in some sense it's like an off policy also, because you are deviating from the actual policy, which was supposed to be strictly the minimum of the Q values, the control that gives you the minimum of the Q values. But then with this, you are kind of saying I may go off my policy, my prescribed policy, which was supposed to be minimum. Okay, so in this optimistic variant of updating of these parametric Q values, this is the way to update. So basically this R is the weights of the network or the parameter, and RK plus 1 is obtained as RK minus this thing, right? So gamma K is, you can think of gamma K as step length. So if you have done gradient descent, then this is gamma K is the step length, and then remaining term is essentially the direction that you will follow. So this is the gradient of the Q tilde. It's like essentially how this. So this is kind of the loss function. So you want to go in the gradient direction of the loss, opposite of the gradient direction. So this is a minimization problem. Gradient gives you direction of the increase, and you want to minimize, you go to the negative gradient direction. So that's why you see this overall, you see this negative of the gradient in this. Okay, and it's kind of scaled by these remaining. There is another view which aligns very precisely with gradient descent. So this is one way you can do the update. It's essentially gradient descent to solve an optimization problem. With respect to the variable r, we have this. So this is more about I am fitting a q values to some data. Now what is the data? So let us look into more detail of this. So this is one update rule where I'm trying to fit q to some data, right? So one possibility is like what could be a good how should I define this as a loss function, right? So what is that loss function which I minimize? The corresponding gradient descent looks like this, right? So basically you look into this and take a square of this. If you look into this, so the whole idea now is what is the loss function that if I apply gradient descent, I get this as an update rule. So let us say loss function is, so as you can see from here, if you think, it is as if like our loss function is like this, which is q tilde ik uk rk minus, basically I have to copy and make a square. I think you get the hint, right? So it's a very simple q tilde ik plus 1 uk plus 1 rk, and you square it, right? Do you make sense of this? If I take this loss and I apply gradient descent on this, so did I make any mistake? Like apply gradient descent here, does it make sense? So apply gradient descent, and this is a loss as a function of r. Okay, so one more thing we should do is kind of make this a generic r, because we are and this is a loss of r. Does this make sense? So this is our loss function, right? Now what does gradient descent method? So our optimization problem is minimize the loss with respect to r. This is the problem we are solving. So the gradient descent tells us, or the stochastic gradient descent, if it's one sample at a time, or like mini batch kind of thing, but that's just a simple thing to do. But the main thing is like this is a gradient descent. So gradient descent update will be r new will be r old, but this is like it's a minimization problem, so we have to go in the negative gradient direction, right? Where negative gradient direction means we are decreasing the function, right? So minus grad of loss with respect to r evaluated at r old. Now only thing that is missing for us is this part. What would be the gradient of the loss with r? So this is a square, right? And so if you take a gradient of this with respect to r, this is a constant, this rk is a constant. So this rk is a constant. So this is like ux square, right? Fx is ux square. So gradient of fx is 2 ux u prime x, right? This is the chain rule thing that will apply here. So we will apply the same thing here. So if you apply same thing here, so gradient of the loss will be 2 times of this. Now you will say, I don't see 2 here, right? But that is a cosmetic thing. We can observe 2 in the gamma, or I can say that my loss was actually like this, 1/2. So if we take a gradient of the loss now, so gradient of the loss with respect to r is 2 times. So let us say 2 gets cancelled, and so this whole term will be there because this is u, right? The whole term. So that whole term will be there. So let us say this is defined as u r, right? Because I don't have much space, right? So basically, and then inside of the u prime. So this is like constant with respect to r. This is constant. So let us say ur is the whole thing, right? You get that? So ur I copied. Now I am my thinking is now I am next step is u prime x. So now I have to take a gradient of this ur with respect to r, but these guys are 0 with respect to r because this is a constant with respect to r. This is a constant with respect to r. So basically I am left with gradient of these first term. So q tilde ik uk r, but this has supposed to be on r old. R old is rk, right? So I put rk back here. Okay. So and ur was this thing here that I just said. So this is exactly of this form. Okay. So from optimization point of view, what we see is is this way of updating the parameter is nothing but minimizing this loss, and this loss is like you can also make this inside bracket, and then this you put plus here, and then this whole thing closed. So basically this is trying to predict this in the loss, right? So this is my parametric network parameterized by R is predicting this as a level. Okay, so so this is what it's trying to do, right? Where gamma is a positive step size. Obviously, typically we use gamma as positive step size, typically between 0 and 1, or at most 0 to 2. So this is nothing but gradient descent, and you will see that there are many variations of this. So this is nothing but SARSA algorithm. So this is SARSA because it's like state, action, and then reward. We look at reward, and then we take next action. So SARSA, right? So state and then action again. So that's why this algorithm is called SARSA. Okay. So if we look into some remarks. So if we look into some special cases where the Q value is a linear in kind of it's like features times the parameters. So if it is of the linear form, assuming the features have been obtained some way, right? So this is the decoupled view that we were talking about, right? So there may be a neural network that produces these features, and then from there we say, okay, these are the features. Now I want to fit these features. So these are the phi values, and then these are my parameters, and then I do a linear combinations to get Q tilde and so on, right? So let us assume that these features are obtained, and then we are looking at a linear model where these features inner product with R. So this is a linear feature-based architecture. So in this case, like, is there a simplification because we saw gradients and so on here? So what will be the form of these when we have this linear model? Okay, so we want to derive this special case. So this is a linear form, and then then in that case, the gradient that we saw in the previous slide, gradient of the Q tilde will be just the phi, just a feature. Okay, so gradient of the Q values are nothing but just features, because gradient of this with respect to R is just phi, right? So that's just phi. So in that case, the update for the parameter simplifies. So basically, your gradient of Q tilde that was here previously, UK RK, is just this guy, and then remaining terms also, wherever Q was there, Q tilde was there, you replace it like this. So here it was Q tilde, so we replace it like that, and here it was also Q tilde. So it is of the linear form, so we replace it like that. So basically, for the linear case, we have this kind of, you can say, a simplification. So thus, what we see from here is that RK is changed in incremental gradient direction. So again, the view that I showed you in the previous slide, I will repeat it here, that for the linear case, again we can think of error like this. In this case, our error is like this, and as if we applied gradient descent on this error. Okay, so you do the same calculations like gradient and so on. So since I proved it for general case, special case works straight away, right? So then so this is nothing but gradient descent. So is it stochastic gradient descent? Right? That's like the thing, right? So do you consider this? What is stochastic gradient descent and what is gradient descent, right? So stochastic, it depends like how I define the loss. So in my loss, my original loss could be like sum of all the losses over all the samples. So that's like the actual loss. So if you look into machine learning problems, then we have samples like xk, yk. Then our loss functions are like some, let us say small n. So some loss function that compares xk and yk, and our total loss is sum over these k, 1 to number of samples. So this is our actual loss. But when we try to learn this, then, so in this case we can also throw in some parameters like R that we want to learn from the training data. So then again, as you see, when you have to minimize this loss, then typically we don't go for like the full batch. By full batch we mean like all the samples. Now the same thing applies here. When we define these errors are for our sum of the samples. Okay, so if you see this error here, then if this error is for only some of the samples, then it is stochastic gradient descent. But if you have this error for like all the samples, like all for the current state k, and then I have like all possible controls I'm thinking of. So for the current state k, all the possible controls, and then I look at what is my my difference from the actual the levels, which are these. So if I sum them up, then it will be like a full batch gradient. If I don't if I do it for samples, then it will be just stochastic gradient descent. Typically it will be stochastic gradient descent, okay, because typically we don't explore all possibles. So again, as I said before, this is again gradient descent, stochastic gradient descent for this error, okay. And of course, since this is an additive method, you will keep doing this. You will keep repeating this. So this R that you have will keep improving. So so you have to do it multiple times. So overall, SARSA, if you know the one that we have is like this. So we have state, action, reward, and then we get to the next state and next and so on. So that's why it's called SARSA. And we usually apply greedy policy when we are training. Then as I said before, we pick some controls randomly and with some probability, and then we select those actions and so on. So, but then there is another algorithm which is a variation of SARSA, and this says that you select an action with the highest Q value. Just to give you a remark that in our notation, which we assume dynamic programming framework, we maximize Q. Minimize Q. We minimize Q, whereas in RL literature they work with reward, so they kind of maximize Q. So typically in dynamic optimization textbooks, and if you go to RL textbooks, dynamic optimization guys use cost, which is minimizing is better, whereas RL guys use reward, so which is maximizing is better. So with this slight like change, highest to lowest in our case, so you will see a minimum of the Q values, and that then you get to something called Q learning. So we can derive Q learning right here, where we put a minimum rather than this here, right? So here we substitute by minimum of the Qs. So obviously, as you can see, computing minimum is like more costly. So I have to do minimum of various possibilities, various use, and then look at minimum of that. So if I put a minimum of the Q tilde of I of the G plus alpha I and so on, then it is Q learning. Okay, so this is the thing. That's the difference between. So overall, this is good because then you can have a model-free implementation here. So this has become quite promising recently. This type of methods like Q learning or SARSA. So we can generate these data via simulator, right? So and compute this and generate this data. If you have a model in hand, then we don't need that, but otherwise we may have to do these simulations. So this is what is SARSA, I said. When Q factor approximation is utilized, their behavior is complex, that's what is observed, and the theoretical convergence bound is also not well defined. Like with the Q factors and let's say Q learning, the theory is like not very like why this method should work. Still these are open problems. So if you take interest in that kind of maths, then these are still open problems like proof convergence bounds of why Q learning methods will converge. The new policies will be like what is the guarantee that these Q values will converge and things like that. So the theoretical convergence is still a work in progress. There are like some results, but it's still very complex in general to derive in a very generic setting. So in practice, SARSA is commonly used in less optimistic form, where state control transition samples are batched together and averaged before producing the parameter vector R. So basically, you would like to work with a lot of samples and batch them together. So in the update rule that we saw, don't just do it for one sample. It's a good idea to consider a batch of samples. So one possibility is that you use these when you store these generated samples in a buffer, okay, and reuse them. Okay, so one possibility that we saw, as I said before, if you go back and then it's like as if we do sample by sample, but then like here we have these kind of sample by sample data being generated, but why not save those? Okay, you did a lot of these, you save these in some as a data, and so this is called experience replay, which is used. So rather than doing one sample at a time, store generated samples in a buffer and reuse them in a randomized fashion. Okay, so this is called experience replay. So DQN was developed by DeepMind, and they use this experience replay, and they also showed this in a Atari game. So this is the first time they showed how DQN can be used in Atari game. So if I have to show this, yeah, so this is the Atari game. I think most of you know this. So basically you have to kind of remove all the bricks here, and this ball should not like go down, right? So you have to kind of keep bouncing it upwards, right? And if you are an expert, then you will do it in a way that that can exploit some gaps here, and maybe trap it somewhere here. Once it gets trapped in one shot, it can kind of keep bouncing and remove many things. So actually it learns that, I think here, so after 240 minutes of training, this is where magic happens. It realizes that digging a tunnel through the wall is most effective. So now it learns that it will create a tunnel so that it becomes a trap for the ball to go in and then do a lot of bouncing. Okay, now it got the tunnel. You can say intelligence. These are intelligence or strategies learned by pure RL methods. There is no one is telling the agent or the software to play it like that.
AI can learn like you playing a video game? It's called reinforcement learning and it's booming. Imagine three AI trying to escape a maze. They explore, make choices, most get lost, but one finds the exit and gets a reward. That's reinforcement learning. The AI learns from trial and error, getting better each time. The DeepSeek team supercharged this. Their DeepSeek R1 paper shows how reinforcement learning can create AI that's amazing at reasoning, even better than some older huge models. Reinforcement learning shines in areas where there is a clear right and wrong. Think math problems, writing code, or playing games like chess. The AI can easily see if its actions lead to success or failure, making it perfect for those kinds of challenges.
So this is the power of this, and this is now seen in reasoning as well. So LLMs produce a lot of these data chain of thoughts, and then there is an RL that will say, okay, I will give you this reward because you are thinking well. I will give you high reward because you thought it this way. So this is how you see RL has become very powerful. Just reward-based model. We are not doing very high quality, maths in this course so far. But you see the power of these methods, right? They really solve so many problems. So that's about. I mean, they were the ones who first kind of used neural network on a large scale. So with experience replay. So that's why this deep RL kind of started from this paper. Okay, I mean in a big way it started from this paper. People were trying in some way, but these were the times where like kind of they solved some big problems using these. Okay, so this is the paper where they describe DeepQN in detail. This was in 2015. So if we look into DeepQN, it's a very simple idea. Okay, so we can do this. So if you want to see outcomes as a table, so I have an state ST, and then I took an action A1, I got the Q values S1 Q S1 A1, or I took an action A2, then I got the Q value S1 A2. So this is the data we are talking about, right? So this is the data. If this grows quite a lot, right? If this table is kind of finite, if it's like even 100 by 100 matrix, there are 100 states and 100 actions, then it can be used as a lookup table. So you can go and say, okay, I'm at this state, and then this is the optimal action to take. So it will be a retrieval problem. You just pick from the table. But the whole problem is that when you play games like Atari or something, the state space and all these are so huge, controls that you can take are so huge that this table really is not possible. Okay, so then you are like, okay, I have seen some states, I have seen some actions. There will be states which will be somewhere in between one of these states. So can you interpolate for me? Can you like predict for me that what is your experience of seeing something similar in the past? Not exactly the same thing in the past, but something similar, something that was neither S2 completely nor S1, but maybe a bit closer to S1. So what can you say? What can you kind of, for A1 action, what do you predict for me? So that will be Q tilde, the approximation. So that will say, okay, I think the Q value is like Q tilde S2. Let's say there is this new state which is kind of like not seen during training, but then I encountered, and then but then based on the training data I build this approximation function. So this gives me liberty that now, just like usual machine learning, that during test data I may get something not in training, but still it is giving me some approximate outcomes of the Q values, which is useful for me. Okay, so this is why this deep QL became very popular, because many problems are like this. Table is not really finite. Okay, so you just like images, right? So you train on cat images, but then someone gives you a new cat image which was never seen in the training, but still the network kind of predicts that it's like a cat. So all this is the power of deep learning used in RL, and this is exactly the point where RL became very popular. Until then, it was not really powerful. Okay, it was doing some simple tic-tac-toe games with finite like states and so on. But beyond that, it was not really powerful. But all the algorithms that you see, all the complex games like Go, chess, all this is now done with this, something similar to this. You throw in some neural network and RL and so on. So this is furthermore here it's about in Q learning you have experience replay. So this is their kind of thing, rather than doing one. So you kind of like you play a lot, and then you have these things, state action reward and so on. You just store them in some replay memory, and then you use that. So store the current transition, put this in a replay memory, and then you can sample these transitions, or you can use some mini batch. So this is the whole DQN algorithm. So remember that in our case we always work with the min, and in RL literature, this figure is from the RL literature, so they use max because it's about maximizing rewards. So this is the loss that is used. So as in the DQN, so this is the loss they use. So this is the network they are learning. In our case, it was R, and here they use theta. In our case, this term was in the beginning, and this was here. So these are the slight changes that you can see. So the network that you are learning is for this guy here. This has the parameter theta, and this is the level that we are trying to predict. So DQN is about minimizing this loss. So this is the DQN loss. So this is our target. This is our action value, and so from the replay memory we can take some samples, and then for that sample the target network says like this is your target, and then the Q network, the current one that you have right now, will have this, and then you minimize the loss for this theta. So you kind of feel like you keep doing this. Basically, you are training the theta. Okay, so you keep doing this, and then periodically you kind of clone this network to become the target. It is kind of like a moving target problem, right? It's optimization problem, but your level itself is moving, improving. This is not an easy optimization. It is not like a static optimization problem, right? This target is like theta minus. It's like the old one.
In RL, the loss may go up, and it is not a bad thing.
Average reward goes up, but why does loss goes up?
Unlike in supervised ML, where loss is a function of parameter during training. In RL, loss also changes as it sees more data.
That is, loss used at previous step was trained on training data coming from different distribution than loss used at current step.
Because the target that you're trying to minimize, to approximate, that itself is like improving over time. So this is my current network, and with this I am trying to kind of get an estimate that what could be a good Q network, and then I'm using this target network, and then after some time, let's say C number of steps, I clone this to become this target network, and then I continue with this, and then after some time again I clone back, and that becomes a target network. Okay, so this is like overall kind of very fascinating that it works, because even my target is changing over time. Okay, so from like convergence point of view, it will be a very that is the reason why there is like proof is not very easy, right? Because it's not like even usual static optimization problems are so tough. Here you have like neural networks involved, and the target itself is moving, so that makes it very challenging. But nevertheless, this became very it works in practice. So as an initial thing, usually it is the case, or many times it's the case, that engineering comes first and theory comes later. So you have to have an open mind that you will play. Okay, there are many things like this. So airplanes were discovered first, like an engineer, and then theory came later. All this aerodynamics and all this maths, Navier-Stokes, all this turbulence theory of turbulence and all this. There are fat books, but that came later. First, someone made a plane, and then something came later, right? Even if I remember Thomas Edison, who invented bulb, he was mostly doing engineering first. He created bulb, but I don't think he knew a lot about thermodynamics or electricity theory and so on. So there is this thing where in many things you will see engineers kind of go well ahead, kind of create things which are very practical and interesting, and then maths comes later on and then kind of refines it more. So it becomes better with maths, but typically it's like the engineering kind of like happens faster. Like LLM is a pure engineering. Like there is no real guarantee for maths or something. There is a transformer. No one really knows like theoretically what it does, but then people kind of like then try to kind of justify and so on. So this is the DQN algorithm, which is kind of very, as an algorithm, it's like not very complicated. So this is DeepQ learning with experience replay. So you initialize the replay memory D to capacity N. So basically in experience replay, like what is the capacity of your, this database or something where you will store these. So this will depend on the memory. Depending on what kind of GPU you use, you will set a parameter. Okay, my replay buffer will be of this size and so on. So then initialize action value function q with random weights. So this is the network that you are trying to learn, this q network with theta as a parameter. So initially, as we know in typical even in machine learning and so on, these neural networks start with random weights. Okay, or you can initialize. There are some initialization tricks that you may try, but otherwise you start with some random weights. Initialize target action value q hat with the weights theta minus is theta, and then so initially it will be like even theta as well. And for episodes 1 to m, do initialize the sequence s1 x1 and the pre-process sequence phi1 s1, and then for t equals 1 to t with probability epsilon, select a random action at. So this is where you are selecting the action randomly. Otherwise, so this is a choice you have in hand. Either you want to explore, then you select an action with some randomness, or you go for the max. So when you go for the max, you are exploiting. Okay, so there is this exploration thing, right? Exploitation or exploration. Okay, so this is like child, right? So sometimes you will see child just randomly moving around without any sometimes it looks like there is no objective. So that's where they are exploring. They are randomly doing things. They are throwing away books, maybe learning gravity, things like that. And then there are cases where they are going for the straight way for their objective. Like if there is chocolate in the fridge, they will go straight to the fridge. Okay, there's like no. So that's the exploitation, right? So they know where is the object that they want. They will go. So this is the thing basically in RL as well. When you exploit, when you explore. So here we have two possibilities. Either we explore with random action, or we select the best. Then we are greedy, right? And then execute action AT. So either with the exploration or the exploitation, execute action AT in the emulator and observe the reward RT and the next state. So in this case, they use the word image because they were working with the Atari game. So in the Atari game, the state is like one image. Okay, so one image, full image is a state. features are extracted via CNN. Okay, so that will be kind of like the pre-processing that is happening. So you may think of this phi that is being processed is via some CNN. So state as S1 equals to X1 was an image, then this image went through CNN, and that produced features which are some vectors which are important features in the Atari game. So then this queue works with those features only, and the processed features, and then action, and then this theta is there, and execute the action 80 and absorb the reward and the image xt. So then set this st plus 1 as st80 xt plus 1, and then pre-process this again. So you get to, let's say, next image. So basically you took some actions in the Atari game. Maybe let's say the ball bounced off, and that's your new image. And then you extract the features, and then you store this transition that you have in the database D. So the new features that you got to from phi 1 to phi t plus 1, that goes into the database, and then sample random mini batches of transitions from the database. Now you have the database, you sample from there, and then you set your target, which is yj, the level, to be other rj. If it happens to be the case that it is really at the terminal step, then that's just some terminal reward rj. If not, then there is a possibility to go a bit further. So this is the further part. So rj plus the remaining cost approximations that you have with the target network. So target network has this theta minus value that's stored there, and then you perform the gradient descent on the target value from the target network, and then this is the network that you are training right now with theta, and this is the square here. So this is the squared loss with respect to the parameter theta. So you do gradient descent and so on, and you get exactly the update rule that we saw before. And every c steps you clone this that we saw in that I told you before, that your target network gets cloned by the current network queue. So this is what we saw here. So this is the cloning part. After every c steps, your target also changes. Okay, so target network changes. Basically, you clone. It's like just copy it. They are actually the same network. So you can just copy it. Okay, so this is the copying part. Okay, so this is the deep QN with experience replay. So apparently experience replay works quite well for them. I think I don't want to go to the POMDP now, so I prefer to stop here.